Okay, so just by simple observations without doing much mathematical computation, we can derive the equation of state. Now, the more difficult part will be how to relate the energy to the temperature. So in order to do that, well, we will have to calculate what this function is. So let's go back. This is what I need. So we need to calculate, this is the volume in a 3n dimensional space. This is always a place where I kind of am indecisive about what to do. This is a straightforward mathematical computation, so it gets boring. But at the same time, I feel that you have to do it at least once, you see it in the classroom at least once, so I'm more tempted to calculate to all the details of this computation. So we have to calculate, well, basically this integral. Well, the easiest would be to calculate this in spherical coordinates. So this will be, well, I don't know the 3n dimensional solid angle. So let me just write the 3n dimensional solid angle. Then we have the integral over the magnitude of our vector, 3n minus 1. And the magnitude changes from 0 to square root of 2me. Well, the integral over the magnitude is kind of trivial. This will be equal to from 0 to square root of 2me, or this function f of e is equal to 2me to the power 3n over 2 divided by 3n d omega 3n. Now, what is this 3n dimensional solid angle? Well, you can try to write it in terms of the integrals over your coordinate, over your the angles, the sine, and there will be sine and cosines. But instead of that, let me look at a different integral whose results I already know. So let me look at this integral. Well, this is p squared is p1 squared plus p2 squared plus p3n squared. I'm just taking into account the components. So I can write this as the integral over p1 from minus infinity to infinity e to power minus p1 squared. The integral over p2 of e to power minus p2 squared from minus infinity to infinity. The integral over dp3n minus p3n squared. So what's the result of each one of those integrals? Square root of pi. So this integral is pi to the power, I have 3n of them, 3n over 2. This is the result of the integral I'm looking at. But at the same time, I can try to evaluate the same integral in spherical coordinates. Well, if I do the same trick, then I have the integral over the solid angle times p to the power 3n minus 1 e to the power minus p squared. This goes from 0 to infinity. Let me make a change of variables. Let me call p squared some other symbol x. Now, the reason why I'm making this change of variable is this. I know the result of this integral. This is the definition of the gamma function. For integers, it's just a factorial. I already know the result. So let me try to convert that integral, the integral over the magnitude to the gamma integral. I can do that by this change of variable, or p will be just square root of x, dp will be square root of x over 2 square root of x. So this integral I, which we had already shown to be pi to the power 3n over 2, will be equal to my 3n dimensional solid angle times, well, dp is dx over 2 square root of x, and then I have x to the power 3n over 2 minus 1 over 2 e to the power minus x. Well, if I do the simplification, this dividing by square root of x will convert this to minus 1. So this is 1 over 2 gamma 3n over 2. Pi to the 3n over 2 is this integral over there. So this integral over the solid angle is twice pi to the power 3n over 2 divided by the gamma function. Now I can go back to my original problem. This is what I was trying to evaluate. So this is equal to 2me to the power 3n over 2 times 2 times pi to the power 3n over 2 divided by gamma 3n over 2. So sigma E, this is the volume occupied by all the microstates having energy less than E, is now V to the power 3n, 2me to the power 3n over 2, twice pi times 3n over 2 divided by gamma 3n over 2. So remember, we were interested in this omega E. This is just the derivative of sigma with respect to the energy. This is, let me write it in this form, e to the power 3n over 2 minus 1 times some other function of n and v. You can calculate that function. It's just those factors of pi's and gammas, etc. So the entropy is a function of energy, is the Boltzmann constant times logarithm of omega, which is Boltzmann constant times 3n over 2 minus 1 times logarithm of E plus some other term which doesn't depend on E. It depends on the number of particles, the volume, etc., but it doesn't depend on E. Well, this 1 over here is negligible. Remember, 3n over 2 is some number of the order of 10 to the power 23. If you add 1 or subtract 1, it practically doesn't change. So this is 3 over 2 n kb logarithm of E plus some other terms which don't depend on E. Now, derivative of the entropy with respect to energy, keeping volume, the number of particles constant, well, thermodynamics tells us that this is just 1 over the temperature. But if you just look at the expression for the entropy, we found this is 3 over 2 n kb over E. I just took the derivative. The terms that I didn't write, well, they gave 0. So energy of the ideal gas is 3 over 2 n kV times T. So this was also an expression that we used on our first week when we were studying the ideal gas. Well, this is somewhat a bit more complicated, but still not that much. But of course, keep in mind that we have made an assumption over here about the energy. Well, we made several assumptions, in fact. You see, when I wrote this expression over 3n particles, and I said that the particles are not interacting with each other, I ignored any possible contribution to the energy from their internal structure. So P and Q is nothing but the position and momentum of the center of mass. There is no rotation and nothing. So this is this is an ideal gas made up of point-like particles, and in fact that is why we have this 3/2 nkBT over there. So let me go one step further. Well, I will write down the general expression of the entropy, but when I take the logarithm, well, there is the gamma function over there, which I need to somehow simplify. Let's also derive the Stirling's approximation. Well, when we study the saddle point approximation, you will learn to do it a bit better than this. But let's look at logarithm of n factorial. Yeah, you see, this is logarithm of 1 times 2 times 3 up to n, which is nothing but logarithm of 1 plus logarithm of 2 plus logarithm of n, I from 1 to n of the logarithm of I. Let me plot this function. Well, 1, 2, 3. Logarithm of 1 is 0. Logarithm of 2 is some number over here. Logarithm of, well, let me show it somewhere over there. Logarithm of 3 is somewhere over here. And so on. Now, logarithm of 1 is 0. Let me use a different color pen. Logarithm of 2 is this height. So logarithm of 2 is that area, because the width of that area is 1, the height is logarithm of 2. Logarithm of 3 is this area. Logarithm of 4 is this area. So this is the area of here is logarithm of 1. The area here is logarithm of 2. The area here is logarithm of 3. The area here is nothing but logarithm of 4. Well, when I sum all those areas, I am essentially calculating an approximation of, this is logarithm of I, of the area below this curve. So this basically tells me that, logarithm of n factorial, which is I, logarithm of I goes from 1 to n. This is approximately the integral of logarithm of x. X goes up to n. Let's say from 1 up to n. Well, what is the integral of logarithm of x? This is the indefinite integral of logarithm of x. X goes from 1 up to n. Well, if you like, it's even from 0 up to n. This is n times logarithm of n minus n. Well, if you put 1 over there, it doesn't make any difference because the answer just changes by 1. And keep in mind that the small n is some number of the order of 10 to the power 22. So this is the Stirling approximation we will use. Well, let's go back. I already have the expression of the volume of states having energy less than E. Gamma 3n over 2 is 3n over 2 minus 1 factorial. Logarithm of gamma 3n over 2 will be approximately 3n over 2 minus 1 logarithm of 3n over 2 minus 1 over E, which will be approximately 3n over 2 logarithm of 3n over 2e. This is what I will use. Now, omega of E was basically the derivative of sigma with respect to E, which is v to the power 3n 2me to the power 3n over 2 2 pi to the 3n over 2 times 3n over 2 e divided by gamma 3n over 2. I just took the derivative. I mean, that last factor 3n over 2e is from the derivative. Now the entropy kb logarithm of omega e, which is, well, 3n times logarithm of v plus 3n over 2 logarithm of 2me plus 3n over 2 times logarithm of pi, these twos also cancel, plus logarithm of 3n over e minus 3n over 2 logarithm of 3n over 2 2e. This is the gamma function in the denominator. Well, let's look at these numbers. This is negligible. Remember, all the other terms in this expression has a factor of n in front, so they are numbers of the order of 10 to the power 23. Logarithm of n is just 23. Logarithm of e will be more or less the same number. Now, in fact, E over n is the energy density. It's a reasonable number, let's say. Not a huge number. All the other terms are huge. So that's negligible. Well, let me combine all these results. It will be 3n times logarithm of v times 2me pi 4me pi small e divided by 3n to the power 1/2. This is the entropy of my ideal gas in terms of its energy, the volume, the number of particles, etc. Now, if you don't like the energy, we already know how energy is related to temperature. You can also relate this to temperature. Let me put this weird sign. Now, the reason is, you see, I said that sigma E was equal to d cube p d3np d3nq. Well, this is not the number of states, this is the total volume. Now, if I want to convert this to the number of states, I have to divide this volume by the volume occupied by 1 microstate. Let me call that number omega 0. So I will have omega 0 to the power n. Omega 0 is some quantum of volume in phase space for a single particle. Well, that will bring here a factor of omega 0 to the power n over 3. That is one thing we have to keep in mind. Now, let us, before looking at what this omega 0 is, let's look at a different problem. You see, this number, this entropy is, it has 3n times logarithm of v plus 3n times logarithm, 3n over 2 times logarithm of e over n plus some constant. This is the entropy I have. And that constant is independent of v, independent of n, independent of anything. Let's say that I have a system that has n particles, is in a volume v, and has an energy E. Then I have an identical system with the same number of particles, same volume, same E. Let's say that this has an entropy as 0, this has an entropy. It will also have the same entropy. So the entropy of the whole system having 2n particles, having a volume V, having an energy E, will be twice S0 or twice SNVE. Yeah, we already talked about extensive quantities. Entropy is an extensive quantity, so if you just double your system, the entropy should be doubled. Now let's look at this expression over here. The left-hand side will give me 3 times 2n logarithm of v, logarithm of 2v, plus 3 over 2 times 2n logarithm of 2e over 2n, plus constant. Well, sorry, that n times some constant. You see, there is this overall n. That constant depends on n. 2n. This is the left-hand side. The right-hand side is twice 3n logarithm of v plus 3 over 2 times n times logarithm of e over n plus constant times 2n, and thermodynamics basically tells us that since S is an extensive quantity, this has to be 0. Well, let's see. No, this is not 2n. Well, with the overall factor, these cancel if I take the difference. There is an overall 2 in the second term. Well, these two cancel, but the first terms do not cancel. I have 6n times logarithm of 2 times the Boltzmann constant. Let me write divide by kb. So this expression over here, we calculated it using statistical mechanics, but it gives us the equation of state. It gives us how energy depends on the temperature. It makes correct predictions verified by experiment. But when we look at whether this entropy is an extensive quantity or not, it's not. It's not an extensive quantity. For it to be an extensive quantity, you see, the problem over here is E over N, that ratio. If you double the system, it doesn't change. If you triple the system, it doesn't change. There's an overall N, which gives that term over here, there, its extensive property. If you look at this term, well, the same thing. It has an overall N dependence, and all the other terms are, that term is constant, so that's an extensive quantity. But if you look at this term, it's not an extensive quantity. Because for that term to be an extensive quantity, I have to divide V by N. If instead of that term, I had this term, instead of just V inside the logarithm, if I had V over N, if I double the system, V will be doubled, N would have been doubled, V over N would have been the same, so there wouldn't be this factor 2 over there. So there's a problem, but the solution is also over there. You see, I should have, if I want to correct this, I have to subtract, let's say, correction, delta S. I have to add, well, if I want to add just that term, I have to add minus 3n logarithm of n. I have to add that term. Well, let me play with this a bit. Well, let's say that it's not just n, but it's 3n. This will also solve my problem. Because you see, it won't be v over n, but it will be v over 3n. Well, that's fine with me. Well, as we are adding terms that depend only on n, let me also add the 3n over here. This also will still solve my problem. If I add this term to my entropy, it will solve my problem of the entropy being extensive. 2, it will not affect the derivative with respect to temperature. 3, it will not affect the derivative with respect to the energy. So it won't affect the equation of state. It won't affect how energy is related to the temperature. It will make my entropy an equation of state. In fact, what I'm adding here is a constant if I'm not changing the number of particles. Well, does this look like something to you? Let me make one correction. Okay. This was kind of bothering me since the beginning. This is not v to the 3n, this is v to the n. All the way. I think I started with v to the n. Yes, here I started with v to the n, but then your question confused me about the 3n. It's v to the n. Now, what will it change in all these results? So this is v to the n. Well, nothing changes here. So this is just n. This is just n. This power is 3 over 2. This is omega 0 to the n. There is no 3. This is just 2. So there's no 3 here. I don't want this 3 anymore. Okay. Now it looks quite familiar. It should look familiar. What is that? Minus the logarithm of n factorial, or logarithm of 1 over n factorial, which basically tells me that take omega, the number of states, divided by n factorial.
Yeah, is this only valid for microparameter in some, because we
Well, I'm not talking about ensembles anymore. I'm just looking at an isolated system, and I'm just looking at the number of states available to my system for the given macro state. I will talk about ensembles probably on Wednesday. For the time being, I'm just playing around, trying to get a grasp of what statistics will be telling me. Now, why do we divide by n factorial? Well, classical physics doesn't give us an answer. But this was known before the advent of quantum mechanics. If you want to have the entropy to be an extensive, the entropy obtained from statistical physics to be an extensive quantity, you have to divide by n factorial. Well, quantum mechanics tells us an answer, and it also tells us that this is just a partial solution to a problem. This is not the exact solution. So the basic idea is, if we have a system of identical particles, how can you distinguish whether one atom is over here, the other one is over here, or if you just exchange them, how do you distinguish these two microstates? Well, classically speaking, you can distinguish them because classical physics allows you to trace the position of each one of those particles. It allows you to trace the trajectory. So you can distinguish all particles. So classically, from the perspective of classical physics, all particles are distinguishable. But quantum mechanics tells us that no, you cannot distinguish them. But that will also change how you count the number of microstates. The state where one particle 1 is over here, particle 2 is over here, is the same state as particle 2 being here, particle 1 being here. That's what quantum mechanics tells me. Now the question is, how many ways I can just shuffle these n particles in n factorial different ways. It's just you have n particles, you can just shuffle them around in n factorial ways only if no two particles are in the same microstate. If two particles can be in the same microstate, then shuffling them, well, we already counted it as one state. But classically, two particles cannot be in the same state anyway. So n factorial is the correction we have. So this is, well, this is called...
Could you repeat why the indistinguishability is related to quantum?
Well, you see, classical physics tells us that you can trace the trajectory of all the particles. So ideally, I can set particle 1 here, particle 2 here, particle 3 here, particle 4 here to start with. And then I can just follow their trajectories. So whether these two particles come like this, or they come like this, I can distinguish them. That is what classical physics tells me. Quantum mechanics tells me that, no, you cannot do that. If they are identical particles, whether they are here or here, if you exchange them, nothing changes. They are exactly the same microstate. So shuffling identical particles around do not give us any new microstate. That is why, at least an approximate correction to this overcounting problem is just dividing by n factorial. Now this paradox, well, you see, we don't have this problem if these two gases that I'm mixing are made up of different particles. Because you see, if I have these different gases, two different gases, if I bring them in contact, allow them to exchange particles, this is an irreversible process. So entropy should increase. And in fact, this is the so-called the entropy of mixing. Just take two separate ideal gases, different ideal gases, allow them to exchange particles, the entropy will increase. It should increase because it's an irreversible process. But if you have identical particles, you see, this is the problem we have. So you have one gas over here, the other gas over here. Well, let me use a different color. If A and B are different particles, removing the separator is an irreversible process. Basically, if you just put back the separator, well, the gas is already mixed, it's not the same as the initial state. But if you have identical gases, if A and B are same kind of particle, removing the separator is a reversible process. Of course, here I'm assuming that the pressures, the temperature, everything else being the same, being in equilibrium before removing the separator. Because you remove the separator, well, the gas is mixed, but they are identical. You put the separator back, and you just recover the initial state you have. So if you have different kinds of particles, entropy should increase. In fact, the increase will be given by an expression of this, which is called the entropy of mixing. But if they are identical particles, the entropy should not increase. And in fact, with this correction, it does not increase. Now, the only task remaining is to obtain the explicit expression of the entropy. Let me also add the Boltzmann constant over there. What is that omega zero? Now, again, classical physics doesn't tell us what that omega zero is. Well, we will derive omega zero from quantum mechanical ideal gas on Wednesday. Okay, any last questions before we go?
It's kind of a long shot. Can you go down a bit? To the A and B part, yeah, here. So I'm imagining a box as a physical separator between A and B, same gases.
Mm-hmm.
But at that point, am I not introducing a new kind of C particle as a separator?
Well, you see, from that perspective, you see the walls are also different kind of particle.
I didn't touch them. Well, I'm touching, I didn't change the orientation or position. Of
So
the walls.
what did you change in the separator?
I removed it and then plugged it back in.
Did you create heat?
Probably.
Is there a friction?
Probably.
Well, if there's friction, of course, that's not a reversible process. But here, this is an idealistic system.
Okay.
Because there's also this problem of the Maxwell's demon. Have you heard of Maxwell's demon? Well, the idea is that you have a separator. You have two gases. Well, you can have the same gas. There is a wall over here. There's a hole. And here you have a demon waiting there. So if an energetic particle comes from the left, it allows it to pass through. If a particle with less energy comes to that hole, it just prevents it to pass through. And it does the opposite on the other side. So that due to this demon, more energetic particles are accumulated on the right, less energetic particles are accumulated on the left. So basically, yeah, even if you start with a system that is initially at the same temperature, well, the right-hand side gets hotter and hotter, the left-hand side gets colder and colder. So how come? How is this possible? Doesn't this happen spontaneously with the action of the demon? And in fact, the resolution led to the information theory. The answer came from the information theory. The basic idea is the demon has some information about the speed of the atoms. And information theory states that information is a physical thing. It's not just some hypothetical mathematical structure. It's a physical thing. And if you want, either the demon has to keep all that information, or, well, that's not possible, or the demon, well, that means the demon has to keep all the information. That means that the entropy of the demon is increasing. or it has to erase the information. Erasing information creates entropy. So this system, although if you just look at the gases, it seems as if the entropy is decreasing by separating the hot and the cold. Still, that is not correct because there is also the entropy in the information or in the erasing of information. Anyway. So see you on Wednesday, still at 1:30. So the homework is postponed one full day.
2 minutes.
1 day. It's just 1 day later. So see you.
We have 2 hours this Wednesday, right?
Yes.
Görüşmek üzere.
Well,